Right now, something invisible is surrounding you. A thin shell of gas so delicate it would fit inside a line drawn on a globe. And once every few years, that shell does something impossible. It reaches across 384,000 kilometers of empty space, and paints the moon red. You've seen photos. Maybe you've watched it happen. But no one told you what you were actually witnessing. You weren't watching the moon change color. You were watching a projection of every sunrise and every sunset happening on Earth, at the exact same moment, broadcast onto another world. This isn't metaphor. This is measurable physics. And it reveals something about your planet that you cannot see any other way. Dr. Noah Petro, NASA's project scientist for the Lunar Reconnaissance Orbiter, puts it bluntly: a total lunar eclipse is the only time humans can directly observe Earth's atmosphere from the outside, using the moon as a screen. Think about that. You live inside something you cannot see. But during a lunar eclipse, that invisible thing becomes visible, written in red light across the face of another celestial body. Here's what makes this stranger: the moon produces no light. Every shimmer you've ever seen, every bright full moon that kept you awake, all borrowed. Reflected sunlight bouncing off gray volcanic rock and 4-billion-year-old dust. During a normal night, sunlight travels 93 million miles, strikes the lunar surface, bounces back. Simple. Direct. But during a total lunar eclipse, Earth slides directly between sun and moon. Our planet casts a shadow into space, a cone of darkness stretching nearly 1.4 million kilometers. When the moon enters that shadow, direct sunlight is blocked completely. The moon should go black. It should vanish against the stars. Instead, it glows the color of blood. Dr. Richard Vondrak, former NASA lunar scientist, explains the mechanism in one sentence: Earth's atmosphere acts as a lens that bends sunlight around our planet and focuses it onto the moon. But not all sunlight survives the journey. Blue wavelengths scatter. They ricochet off nitrogen and oxygen molecules in our atmosphere and spray in every direction, which is why your daytime sky looks blue. Red wavelengths behave differently. They punch through. They bend around Earth's curve and keep traveling. The same physics that turns sunsets orange, that paints the horizon crimson when the sun grazes the edge of your world, that exact phenomenon wraps around the entire planet during an eclipse. 360 degrees of sunset light, focused onto the moon like a spotlight. Dr. Petro calls it viewing Earth as an exoplanet. Because this is precisely how astronomers study distant worlds, watching starlight filter through alien atmospheres, reading the colors that survive. During a lunar eclipse, you can do the same thing. Except the planet is yours. And the atmosphere you're analyzing is the one keeping you alive. But here's what the textbooks leave out: the moon doesn't always turn the same red. Some eclipses glow bright copper. Others burn so dark the moon nearly disappears. In 1992, observers reported an eclipse so dim they could barely find the moon at all. The difference. What's floating in Earth's atmosphere at that exact moment? Volcanic ash. Wildfire smoke. Particles measured in millionths of a meter. NASA can now predict the color of an eclipse years in advance. By tracking eruptions on the other side of the planet, the moon is a mirror. And what it reflects back is not just sunlight. It reflects the current state of Earth's breath. The physics seemed simple at first. Sunlight bends around Earth, red wavelengths pass through, the moon glows crimson. Case closed. For decades, astronomers treated lunar eclipse coloration as a solved problem, a predictable consequence of Rayleigh scattering that any undergraduate could calculate. They were wrong. In 1884, French astronomer André-Louis Danjon began systematically cataloging lunar eclipse colors. What he found destroyed the assumption of predictability. Some eclipses produced a bright copper moon easily visible to the naked eye. Others turned so dark that experienced observers lost track of the moon entirely against the background stars. Danjon created a 5-point scale, now called the Danjon Scale, ranging from L0 to L4. An L0 eclipse means near total invisibility, the moon reduced to a faint gray smudge. An L4 eclipse produces a bright orange moon with a bluish rim. Same geometry. Same orbital mechanics. Completely different results. The question haunted planetary scientists for nearly a century. If the physics is constant, why does the output vary so dramatically? Dr. Richard Keene, a retired atmospheric scientist from the University of Colorado, spent over 30 years hunting the answer. His conclusion redirected how NASA thinks about lunar eclipses entirely. The moon is not reflecting a constant signal. It is reflecting the variable state of Earth's upper atmosphere. The critical zone sits between 10 and 30 kilometers above sea level. This region, the stratosphere, normally contains very few particles. Sunlight refracting through clean stratosphere produces bright copper eclipses. But when volcanic eruptions inject sulfur dioxide into this layer, the gas converts to sulfuric acid droplets that block and scatter incoming light. The 1991 eruption of Mount Pinatubo in the Philippines demonstrated this principle with brutal clarity. Pinatubo blasted roughly 20 million tons of sulfur dioxide into the stratosphere, creating a global aerosol layer that persisted for nearly 2 years. The December 1992 lunar eclipse occurred 18 months after Pinatubo. Observers worldwide reported something disturbing. The moon didn't turn red. It nearly vanished. Dr. Keene measured it at L0 on the Danjon Scale, one of the darkest eclipses in recorded history. Photographers struggled to capture any image at all. This was the first major complication. Lunar eclipse color is not determined by the moon. It is not determined by the sun. It is determined by what humans and volcanoes have put into Earth's atmosphere. Dr. Keene reverse-engineered the relationship. By analyzing historical eclipse brightness records stretching back to 1600, he could identify volcanic eruptions that left no other trace. The atmosphere had been recording its own history, and the moon had been displaying it for anyone paying attention. NASA's Goddard Space Flight Center now incorporates stratospheric aerosol data into eclipse predictions. Dr. Noah Petro confirms that eclipse color forecasting has become a tool for validating atmospheric models. The moon serves as an independent check on satellite measurements of Earth's upper atmosphere. But Keene's research revealed something else, something that complicated the picture further. Volcanic aerosols explained the darkest eclipses. They did not fully explain the brightest ones. An L4 eclipse requires more than clean air. It requires specific conditions in the troposphere, the lowest atmospheric layer where weather occurs. Cloud cover, humidity, dust from deserts, smoke from wildfires, All of these factors modulate the final color. The moon was not just recording volcanic history. It was recording everything. Every particle suspended in Earth's air column contributed to the signal. Predicting eclipse color meant modeling the entire atmosphere from surface to stratosphere, and then researchers discovered the signal could flow in both directions. Here is where the story breaks open. For years, scientists treated Earth's atmosphere as the painter and the moon as the canvas. A one-way transmission. Light leaves the sun, filters through our air, lands on lunar soil, bounces back. Simple. Predictable. Controllable. Then astronomers started pointing different instruments at the eclipsed moon. And what they found changed everything we thought we understood about studying distant worlds. Dr. Enric Pallé at the Instituto de Astrofísica de Canarias had a radical idea. What if we stopped looking at the moon as a moon and started looking at it as a mirror? Not poetically. Literally. A 3,400-kilometer mirror reflecting Earth's atmospheric fingerprint back at us. His team pointed spectroscopes at the eclipsed moon and captured the light passing through Earth's atmosphere. They weren't studying the moon anymore. They were studying Earth from the outside, as if they were alien astronomers orbiting a distant star, watching our planet cross in front of the sun. What they detected in that borrowed light stopped the scientific community cold: oxygen, ozone, water vapor, nitrogen dioxide. The chemical signatures of a living planet, detectable in the faint red glow bouncing off lunar dust. Dr. Pallé had just proved that Earth's biosignatures, the markers of life itself, could be read from 384,000 kilometers away using nothing but reflected eclipse light. Think about what this means for you. Right now, NASA's James Webb Space Telescope is hunting for habitable exoplanets by watching starlight filter through alien atmospheres. The technique is called transmission spectroscopy. Scientists search for oxygen, methane, water vapor, the same molecules that betray life on Earth. But how do you calibrate such a search? How do you know what a living planet actually looks like from trillions of kilometers away? You use the only living planet you can study up close. You use Earth. And the only time you can study Earth's atmosphere from the outside, without launching a spacecraft, is during a total lunar eclipse. Dr. Alison Youngblood at NASA's Goddard Space Flight Center calls lunar eclipses ground truth for exoplanet science. Every eclipse is a calibration opportunity. Every red moon is a test case for the instruments hunting alien life. The moon had transformed from subject to tool, from destination to laboratory, but the deeper researchers looked, the more complicated the signal became. In 2019, a team using the Hubble Space Telescope detected ozone in Earth's atmosphere by observing a lunar eclipse from space. The measurement was so precise it revealed seasonal variations in ozone concentration. The moon was reflecting not just Earth's atmosphere but Earth's cycles, its rhythms, its breath changing month by month. Dr. Giovanna Tinetti at University College London pushed the implications further. If we can read Earth's biosignatures in eclipse light, then any alien civilization with basic telescopes could do the same to us. Every lunar eclipse broadcasts our planet's chemical fingerprint into space. Oxygen from photosynthesis. Methane from biology and industry. Nitrogen dioxide from combustion. We have been announcing ourselves for 4 billion years. The red moon is not just a spectacle. It is a beacon. A signal fire visible to anyone watching from the right angle at the right time. The same physics that lets us search for alien life also lets alien life search for us. And here is the turn you did not see coming. The color of the eclipsed moon does not just tell us about Earth's present. It tells us about Earth's future. Climate scientists have begun using eclipse color records as an independent check on atmospheric models projecting decades ahead. The moon remembers what we put into the sky. And it will keep remembering long after we forget. Let's pull back and see what has actually been assembled here. A phenomenon that ancient humans interpreted as divine warfare has become one of the most sophisticated diagnostic tools in modern planetary science. The red moon connects volcanic monitoring, climate research, atmospheric chemistry, and the search for extraterrestrial life into a single unified observation. Every thread we have followed leads to the same conclusion. The moon is Earth's mirror. And we have only just learned how to read the reflection. Dr. Sara Seager at MIT, one of the world's leading exoplanet hunters, frames it with precision that borders on poetry. She explains that when you watch a lunar eclipse, you are seeing exactly what an alien astronomer would see if they observed Earth transiting the Sun from a nearby star system. Same physics. Same spectral signatures. Same proof of a living world. This is the breakthrough. Not a single discovery but a convergence. Disciplines that evolved separately, atmospheric science, volcanology, astrobiology, have realized they are studying the same signal from different angles. Consider what NASA can now extract from a single eclipse observation. Stratospheric aerosol concentration reveals recent volcanic activity and predicts short-term climate effects. Ozone levels indicate ultraviolet shielding strength and seasonal atmospheric dynamics. Water vapor content maps humidity distribution across the sunlit edge of Earth. Nitrogen dioxide traces industrial and combustion activity across continents. One red moon. 4 independent data streams. 0 additional spacecraft required. Dr. Richard Keen's 30-year dataset of eclipse brightness has become a climate record that satellites cannot replicate. His measurements extend backward through historical observations to 1600, creating a 4-century baseline of stratospheric clarity. When climate models predict volcanic cooling effects, researchers check them against Keen's eclipse archive. The moon has been recording Earth's atmospheric history longer than any human institution has existed, but the synthesis goes deeper than data collection. Dr. Enric Pallé's spectroscopic work proved that biosignatures survive the journey through Earth's atmosphere, reflect off the moon, and return detectable to ground-based telescopes. This means transmission spectroscopy works. The technique NASA uses to search for life on exoplanets has been validated using the only confirmed living planet in the universe. Every lunar eclipse is a dress rehearsal for detecting alien life. Dr. Giovanna Tinetti emphasizes what this implies for the James Webb Space Telescope and its successors. Each eclipse teaches us what signatures to expect, what noise to filter, what concentrations indicate biology versus geology. Without the moon as a calibration target, exoplanet science would be guessing in the dark. Yet synthesis also reveals what we do not know. The precise relationship between tropospheric conditions and eclipse color remains incompletely modeled. Wildfire smoke, desert dust, and industrial haze all contribute to the signal, but quantifying their individual effects requires observations we have not yet made. Dr. Noah Petro admits that predicting eclipse brightness within one Danjon unit remains difficult despite decades of research. There are also eclipses that defy explanation entirely. The January 2019 eclipse glowed brighter than volcanic aerosol models predicted. Something in the atmosphere reflected more red light than expected, and no team has definitively identified the cause. The moon keeps showing us things we cannot yet interpret, and this is where the science leads somewhere unexpected. We have focused entirely on what the eclipse reveals about Earth. But the real question is not what we found. It is what it means to live on a planet that announces its own existence every time it passes between sun and moon. Step outside during the next total lunar eclipse and understand what you are actually witnessing. You are not watching the moon change color. You are watching your planet reveal itself. Every photon striking your eyes has traveled 93 million miles from the sun, grazed the edge of Earth, bent through the atmosphere keeping you alive, crossed 384,000 kilometers of vacuum, bounced off ancient lunar rock, and returned to you carrying information about the world you inhabit. That light has touched every sunrise and sunset happening on Earth at that moment. It has filtered through volcanic ash from eruptions you never heard about. It has passed through smoke from wildfires burning on continents you have never visited. It carries the chemical fingerprint of oxygen produced by photosynthesis, water vapor rising from oceans, ozone shielding life from ultraviolet radiation. The red moon is a message written in physics. And you are both the sender and the recipient. Dr. Sara Seager suggests that lunar eclipses should fundamentally change how we think about our place in the cosmos. We spend billions of dollars launching telescopes to read the atmospheres of planets orbiting distant stars. Yet the same information about our own planet gets broadcast freely across space every time Earth's shadow crosses the moon. Any civilization within observing range could detect us. Not our radio signals, which have traveled less than 120 light-years. Not our city lights, which are too dim to see from interstellar distances. But our atmosphere, which has been scattering biosignatures into space for 4 billion years. We have been visible since before we existed. NASA's future eclipse observation campaigns will deploy instruments across multiple continents to capture the full range of atmospheric data embedded in the red light. Dr. Noah Petro confirms that each eclipse now generates datasets feeding into climate models, volcanic monitoring systems, and exoplanet detection algorithms simultaneously. A single 90-minute event serves more scientific disciplines than most dedicated satellite missions. But the implications stretch beyond data collection. The moon has recorded Earth's atmospheric history with more fidelity than any human archive. Ice cores reach back 800,000 years. Tree rings extend a few millennia. Eclipse records in the lunar reflection theoretically encode every major volcanic eruption, every extinction-level impact, every shift in atmospheric composition since the moon formed 4.5 billion years ago. We lack the instruments to read that deep archive. We may build them within your lifetime. Now return to where we started. That thin shell of gas surrounding you right now, so delicate it would fit inside a line drawn on a globe, has just performed something remarkable. It has reached across nearly 400,000 kilometers of empty space and painted a world red. It has broadcast your planet's vital signs to anyone watching. It has connected volcanic eruptions to exoplanet science to the search for life beyond Earth. And it has done this for billions of years without anyone noticing. Carl Sagan once wrote that astronomy is a humbling and character-building experience. He could not have known how literally true that statement would become. The red moon humbles us by showing that our atmosphere, our life, our existence has never been private. We are visible. We have always been visible. The next total lunar eclipse will cross the sky and most people will photograph it, share it, forget it. But you will know what you are seeing. A planet revealing itself. A mirror reflecting home. A signal that has been broadcasting since before there was anyone to send it. The universe does not hide its wonders. It only waits for someone to look up and understand.